So we should get started any second now. If you are on the phone, if you could mute your line unless you want to ask a question, that would be good.
Okay. Shall we start?
Sure.
Okay. Good morning, everybody, and on behalf of EDA Direct, we'd like to wish you a very warm welcome to this webinar on advanced verification using Questa. The webinar is going to be presented by Walter Goody. Walter Goody has been with Mentor Graphics for over 23 years. He started off as a senior consultant in 1996, and from 2003 onwards has been an applications engineering consultant, and his field of expertise is all of verification, including function verification, formal verification, and everything in between. So without much further ado, I'll hand it over to Walter. Thank you so much.
Okay, and Mario, just you can hear me and you can see my screen and the cursor movement, right?
Yes, absolutely.
Oh, okay, great. All right, well, welcome everybody to today's webinar. Shouldn't be too terribly long, but we're going to be talking about the Questa verification IP today. If you think about most projects, and I'm saying FPGAs on this slide, but even most ASICs, usually these days what's happening is your custom logic is somewhere buried down in the middle of that FPGA, and the I/O onto and off of the chip is generally some kind of a industry standard. So whether it be simple like an SPI or a UART, it could be an Aurora bus if you're in the Altera world. It could be Ethernet, PCIe, serial ATA, any of these, and and a lot of AXI we see. So these standard buses are usually where the I/O onto and off the chip are coming from, and it's your custom logic is somewhere in the middle. So you can do a lot of block level testing of your designs at that level, but if you ever want to run any full chip simulations, you're left then with providing data at these, using these industry standard buses. And especially for things like PCIe, generating that kind of traffic is quite difficult. And having something that can generate that traffic for you is quite desirable. So Mentor has what we call the Enterprise Verification Platform, which is kind of a set of verification tools. The Questa simulator is probably the one that most of you are familiar with, but we kind of have an infrastructure that will connect that simulator to stimulus generation, to results management and analysis, the debug flow, but that simulator is not necessarily the only engine that can hook into that infrastructure. We have a whole set of formal verification tools, which are mathematical property checking tools. On the really high end, we have our emulator, which uses that same infrastructure. And then on these outside things, we have an FPGA prototyping system and a virtual prototyping system. And as I say, they all connect to this same infrastructure. You can generate stimulus to all of these from a common thread. You can look at the debug over the same, with the same debug tools. So that verification infrastructure is one thing, and verification IP is what we're talking about today, falls into that stimulus and debug mostly category. So, every iteration of the different standards gets more complex. So, you know, you need to continue to operate on that. You need to continue to be able to generate data. So just looking, for instance, at the ARM, you know, way back in 95, the APD was a quite simple bus. You could write a bus functional model for that. It was no big deal. As we moved up to APB2 and then, you know, started doing some of the AHB and then eventually the AXI, things have gotten more and more and more complex. On the PCIe side of things, as we've continued to move forward through the different versions, generating that PCIe traffic becomes more and more complex. And, you know, I understand that you are probably not necessarily going to try to test every transaction type on these buses, but you do want to make sure that you have implemented them correctly, that you've hooked them up, that the connection to your devices, and quite honestly, it's not a bad idea to do some sanity check that says, if we want to make sure we can do all of these different types of transactions, let's run those through the device and make sure that everything is hooked up internally correct. So the standards keep getting more complex, and that is where the system Verilog language kind of got set up to standardize a lot of this, to add a random stimulus, which can help uncover bugs that you hadn't thought of. It means that we can now start to create verification IP. And that means that everybody is using the same standard, and that way we can create this piece of verification IP. It can be reusable across projects. It can be reusable from block level to subsystem level to chip level, etc. And so what this verification IP becomes is the UVM agent is kind of the heart of any UVM test bench. That is the thing that connects to your DUT, that you give transactions of whatever type of protocol you're using. That agent then turns those transactions into the bit wiggling, the signaling of that protocol. It monitors the pin activity from the DUT, turns that back into transactions, allows you to do protocol level debugging. So you're debugging at the transaction level, not at the pin wiggle level. And then it allows you to start doing coverage. So you're looking for certain items to be covered. You want to make sure that you've run transactions of different types across your bus, so you can collect coverage to make sure that you've done that. And then if you are doing a full compliance test on a protocol, we have a test plan and we have a test suite of transactions that could totally cover that. Generally, like I said, the end user isn't necessarily interested in that, but they should be interested in generating traffic, and they should be interested in at least making sure that they've done transactions of every type that is going to be in their system. So, you know, what we've tried to do is make these verification components be comprehensive for whatever protocol you're testing, that they have assertions to make sure that traffic isn't being, traffic types aren't being violated, that you can collect coverage for those things, and you can do transaction level debugging. Again, you probably aren't going to do compliance tests, but it is there if you need it. And then to go to the next level of traffic generation, you can even step beyond the constrained random and go to what's called portable stimulus, which is a topic for another webinar. But the whole idea is to get you up and running as quickly as possible, to get you doing productive verification very quickly, and to make sure that you are generating legal traffic, and make sure that your device is processing that traffic correctly. So if we look at our verification catalog as of today, we have a few different families, and we generally sell this verification IP as families, or not generally, we do sell this as families. So if you are doing ARM buses, you buy the AMBA family, and you can generate anywhere from, simple APV, AHB traffic all the way up through AXI 4. We have AXI 5 and ACE 5 coming. PCIe, we can generate all the way up through PCIe 4.0. 5.0 may be released by now. The slide is a little bit old, I think. So, the PCIe family allows you to generate and test traffic of every different type. Sorry about that. I don't know what happened there. The Ethernet family allows you to generate Ethernet traffic. The PCIe, you can do that both at the serial level or the pipe level. Ethernet, same way, you can generate your traffic either at the PHY level or the, my brain's stalling right now. So either at the serial or at the parallel level on the Ethernet. We can pretty much handle all the way up through, now like 100 gigabyte, 200 gigabyte Ethernet. USB serial is just a bunch of the simple serial buses. We have a display family, so HDMI, DisplayPort are probably the most common. Serial ATA, we have a mil-aero family, which is SpaceWire and 1553B. I think we have C now as well. And then we also have a set of memory models. So these can be used if you are using memory in your system. If your device is hooking up to any kind of memory, you can drop down one of these memory models, and it will basically model that memory for you. So that can be done. You say you can do it down to the part level. If you have a particular manufacturer that you're going to be using, you can just do it. Say I have a general DDR2. Again, can people mute their lines if they are speaking in the background, because it's a little distracting? Thank you. So for any of these protocols, you can run a complete protocol compliance test. So we have all the traffic generation, and then all the assertions and all the cover points in there to actually run a full compliance test on that protocol. Or you can go into that test plan and say, you know what I really care about is these certain types of transactions. I want to make sure that I'm, doing certain types of transactions. So I want to make sure that I cover these test plan objects, and then you can run your design and look at the coverage that's collected, and it will tell you whether those test plan objects and thus those types of transactions have been covered. So we start from a test plan for each of our verification IPs. We create a test plan that makes sure we could do that full protocol compliance suite. And then from that test plan, we generate a set of sequences that will fully test that compliance test, and we set up all the coverage information that you need to collect that. So what that does for you is you can use then our verification management system to go in and say, I want to make sure that I have tested narrow transfers, aligned bursts, et cetera, et cetera. So you can pick out the features of, in this case, the AMBA AXI operation. You could pick out the features that you want to make sure you have tested. You could enable the coverage on those features, run your test bench, and then get a report back that says, hey, I've tested that. And then on the testing side of things, on the debug side, you get a protocol, a transaction view of everything going on in your system. So you can put those transactions into the wave window so that you can now look at the AXI bus. You can say, for channel, whatever this is, channel 1, I have done a write. It is channel 1, apparently, because I think that's the channel. Yeah. So on channel 1, I wrote to this address, I wrote this data, and over this amount of time, that write transaction happened. And here was a write to channel 0, and another write to channel 0, and channel 0, etc. So debugging at that level, especially on things like a PCIe bus, where it is a 2-wire interface that is 3,000 clock cycles long to complete a transaction, you probably do not want to have to analyze that serial data stream to make sure that the transaction you were expecting happened. Instead, our verification IP will monitor that, and it will pick out that a write with these parameters happened. You also get a text output log that basically says, at this time, to this address, we wrote this data. To this address, we read this data. So you get a textual output log as well for every one of these protocols. And that's just showing a little more of the signaling. So we've had a lot of successful projects, just a few that we've worked with, Cypress, ST Micro, ARM, Microsemi, another ST Micro. TDLA was an FPGA project. They supply a PCIe piece of IP, and they used our verification IP to harden that a little bit. ARM. So I just wanted to show a few examples. Not going to go into big detail, but again, this is just some testimonial from, for instance, Microsemi, that they've had success, Cypress, ARM. I'll give you these slides. I'm not going to read through all this, but just a few of the success stories that we've had. So I've kind of already said this, that you can do a full protocol verification test, or you can just generate the traffic to get it to the internals of your device. Make sure that you've hooked up the device correctly, that you're using the correct signaling protocols, etc., and have it configured in the way that you would. So this is from some studies that we do on a periodic basis, and it's just showing even, well, this is probably a mixture of FPGA and this is all ASIC. So this is saying on any given ASIC project, 10 years ago, it was about 2 designers per every verification engineer. By 2016, we had more verification engineers than we had designers. I think we'll get the 2018 data very soon, and I expect to see that trend going up. So we really do see the trend, and we also see it in the FPGA world, that more and more time is being spent on verification versus design. And so some of the things that are helpful in that is this broad category of things we call test bench automation. So test bench automation is built up with a few things. So the UVM standard, the Universal Verification Methodology, that has become a Accelera standard. It is either just become an IEEE standard or is about to become an IEEE standard. And that is a standardized methodology for using System Verilog to create a test bench. The reason it is very powerful is it's really thought through the ideas of reuse, both from project to project and from low-level block verification to subsystems to chip to multi-chip verification, that these components are reusable and you won't have to change them as you move from these different levels. The problem with UVM, it is very complex and it's got a long learning curve. So Mentor has created what we call the UVM framework, which is a simplification of some of the class libraries of UVM to make them more easy to use, and also a way to create a template that describes your test bench and then let the code generator go off and pull all the boilerplate code together and create all the make files for compiling and running your test bench. So that's kind of our UVM Jumpstart program, is UVM framework. VIP is another pillar in that it is something that helps you, the VIP is a set of pre-designed UVM agents, but then we've created the UVM configurator and we've integrated that with the UVM framework to allow you to quickly create, configure, and instantiate this VIP within a UVM test bench. And then the final thing is this intelligent test bench automation or portable stimulus, which is kind of the next generation of stimulus generation. So UVM framework, as I said, it's really about getting you up and running as quickly as possible with your UVM test bench. It is a code generator in the sense of, instead of needing to write every piece of UVM code that you're going to use, which can get quite complicated, you can start out by creating a template for each of your agents that describes the I/O of that agent. You create a template that says what agents are in my environment and a template for a test, and then it will generate all of the code and all of the compile scripts you need to get that test bench up and running. So we've found that we can get a test bench up in a matter of hours versus a matter of days. So if you look at a general UVM environment, as I said, the agent is what communicates to your DUT for each of your major communications ports on your device. So you might have, in this case, a generic bus agent that's creating traffic for that bus. You've got a FPU register agent over here that's setting up the registers going into a floating point unit. This FPU reference model is saying, given what I've put into the DUT, here's what I expect to be coming out. You have scoreboards that collect coverage. You then have an environment. So this is for a general, and then for verification IP, we've added the ability to drop those predefined verification IPs into your code generator template so that you've immediately started to get that. So this is back again towards the UVMFs in general. You start from a template right here. You hand that to the code generator that generates your whole UVM test bench and all the make files needed to compile that. As a user, then your task is to go in and fill in the signaling protocol for driving a transaction to the DUT, to monitor the pin wiggles and turn that back into transactions. Maybe some constraints on how the data gets generated, and then add some sequences by extending the base sequence. So I think this first task, we put in this general access task, and then you would go in and change that to maybe a do read and a do write task. And you fill in all the signaling that's needed to do that. For bus transactions, you'd extend that base transaction and give some constraints and set that up. But now let's say you've done a UVM test bench, you want to bring in a verification component. How do you do that? And that is you use this Questa VIP configurator. You say, you know what, I'm going to have an AXI bus. It's going to be an AXI slave. It's going to have a 32-bit address, a 32-bit data. You know, you go in and configure how that's going to look. You hit the configurator, and that generates that test for you. You can put in things like the address map right here. As I said, you can say, is this an AXI 1, 2, 3, 4? Is this a master? Is this a slave? You put in all that configuration, and then you generate your UVMF, or you generate your agent for that protocol. We also give you the set of data you need to say, okay, I want to drop that environment. So I created this sub-environment that had a PCIe, a couple of AXI buses, an APD bus, a few of those things, and then it gives you the strings you need to put that into your UVMF environment so that you generate your whole test bench. This is just an example of, like I said, I had I had a particular DUT here that had a floating point unit. I had these AXI things, and I was able to actually completely use VIP components to hook up to all the external ports of that, and run that through the generator and start generating traffic quite quickly. So our verification IP works with the UVMF generator. So that is the one thing, that all of these verification IP components are UVM agents. So you do need to have a UVM test bench. So Mentor provides the UVM framework to help you get started creating a UVM test bench. The VIP configurator will help you configure those verification components for, you know, whatever your need is, and to integrate them back with the UVM framework. It creates coverage so that you can say what kind of coverage you are interested in, what features you want to test. And it will collect all the coverage to make sure you've done that. It'll create a transaction level stimulus analyzer, so you can put those transactions in the wave window to make sure that things are happening and do your debug at a higher level. Then if you want to go down the path of starting to look at portable stimulus for like next generation stimulus, you can do that. So we really like to think that our verification IP is your one-stop shop. If you have standard protocols that are being used, especially things like PCIe, we have something on the order of 30 man years in our PCIe verification component. If you don't have the time to create that PCIe traffic yourself, our verification IP will help you to do that. So that's kind of what I wanted to talk about real quick today. I didn't think this was going to take a full hour. We have a large library of standard protocols for both bus protocols and memory interfaces. We can rapidly create and integrate those into a UVM test bench and make sure that the protocol is, at least all the features of that protocol that you want to make sure you test it. We can collect the coverage and give you reports on that, and it's all integrated within our Questa verification system. So any questions before we finish here? Let's go back to the... Well, hopefully this was at least interesting and somewhat informative. If you guys do have further questions, don't hesitate to contact me. Why don't I actually go back to that first page? There is my contact information right there. There's an underscore there. So it's Walter_Goody@mentor.com. If you have any further questions, don't hesitate to send me an email or talk to your EDA rep. And if there aren't any other questions, I think we can call this a webinar.
Thank you so much, Walter. On behalf of EDA Direct, we wish to thank all the participants as well for attending the webinar. We hope it has been useful, and yes, as Walter said, you can send him questions as far as any of the matter covered in the webinar. And if you have any questions related to the software, the pricing, things like that, please feel free to send an email to sales@eddirect.com or contact us via our website. Once again, thanks to both Walter and all the participants, and for this wonderful webinar. And we'll hope to see you in the next one. Thank you so much. Have a wonderful day.
All right. Bye.